Have you ever pondered the nature of reality? Do you consider the universe a mere collection of particles, or is there something more? Welcome, dear listeners, to the edge of our understanding, where we wrestle with the grandest of questions and grapple with the enigma that is our universe. Today we delve into the complex and intriguing world of string theory. It is said that the universe writes its autobiography in the language of mathematics, and if that's true, then string theory is a key chapter in that tale. A theoretical framework where the point-like particles of particle physics are replaced by one-dimensional objects called strings, it represents a bold attempt to reconcile the seemingly incompatible realms of quantum mechanics and general relativity. Our universe, vast and magnificent, has long been a source of wonder and fascination. Its mysteries have captivated us, its secrets have eluded us. Traditional physics has taken us far, but there remain questions, stubborn and persistent, that resist our best efforts to answer. Questions about the true nature of space, time, and the fabric of reality itself. And so we turn to theories like string theory, theories that dare to venture beyond the known, that dare to propose new and radical ideas. String theory suggests that at the most fundamental level, everything in the universe, all particles, all forces, is composed of tiny vibrating strings. Yes, strings, infinitesimally small, vibrating at different frequencies like the strings on a violin, creating the symphony that is our universe. It's a radically different way of viewing the world, a perspective that could potentially unlock the deepest secrets of the cosmos. So, as we stand on the threshold of this journey, let's remember that the pursuit of knowledge is a voyage into the unknown. It is a quest filled with challenges and uncertainties, but also with wonder and awe. Let us now dive into the fascinating world of string theory and unravel the secrets of the universe. What precisely is string theory, you might ask? Well, let's dive right in. String theory, in essence, is a theoretical framework in which the point-like particles of particle physics are replaced by one-dimensional objects called strings. It's a bit of a mind-bender, I know, but bear with me. You see, string theory suggests that what we perceive as different fundamental particles are actually different modes of vibrations of the string. Imagine plucking a guitar string. The string vibrates, and these vibrations create sound. Now, replace the sound with the properties of fundamental particles. In the same way, the different notes produced by a string, depending on how it's plucked, could correspond to the different particles. The key idea here is that these tiny strings are vibrating in a whole host of different ways, and it's these different vibrations that give rise to the different particles we see in the universe. Electrons, quarks, neutrinos, photons, all these could simply be different vibrational states of the same fundamental string. Now you might be wondering, if everything is made up of strings, then what are these strings made of? The answer, surprisingly, is nothing. Strings are not made of anything else. They are fundamental objects, just as particles were regarded as fundamental in the old quantum theory. And the real beauty of string theory, it's a theory of everything. It aims to provide a complete, unified and coherent description of the fundamental structure of our universe. That's right, it's a theory that seeks to weave everything in the universe, from the tiniest particle to the largest galaxy, into a single, unified tapestry. So, instead of picturing atoms as tiny balls, imagine them as minuscule, vibrating strings. That's string theory for you. How can we perceive the universe as strings? An intriguing question indeed. Let's delve into the world of string theory, a concept that offers a unified picture of our universe. Imagine the universe as a grand symphony, with each particle represented as a tiny vibrating string. The different frequencies of these strings correspond to different fundamental particles. This is the heart of string theory, a theory that attempts to bridge the gap between quantum mechanics and general relativity, the two giants of physics. Quantum mechanics deals with the world at the smallest scales, the realm of particles and quarks. It is a world of uncertainty where particles can exist in multiple places at once and pop in and out of existence. On the other hand, general relativity is Einstein's theory of gravity, which describes the universe at the largest scales, the realm of planets, stars and galaxies. It is a world of predictability, where everything follows the curvature of space-time. For a long time, these two theories lived in separate worlds, unable to reconcile their differences. They seem to be speaking different languages, each with its own set of rules. But string theory comes along and offers a common language, a bridge between these two worlds. String theory suggests that every particle, every force in our universe is a manifestation of the vibration of tiny strings. Quantum mechanics and general relativity are no longer at odds, but are simply different ways of interpreting the music of these strings. The universe is no longer a chaotic assembly of independent particles and forces. Instead, it's a harmonious orchestra of strings, vibrating at different frequencies, creating the symphony we call reality. The universe is interconnected not through some mystical force, but through the music of strings. String theory therefore offers a harmonious view of the universe where everything is interconnected. It's like a cosmic web where each string is a thread, and together they weave the fabric of our universe. How many dimensions of space do you think exist? We're all familiar with the three dimensions: length, width and height. Add time into the mix, and you've got the four-dimensional space-time that Einstein's theory of relativity is based upon. Yet, string theory suggests that these four dimensions may only be the tip of the iceberg. In string theory, the fundamental particles we observe are not point-like dots, but rather tiny, vibrating strings. These strings require a certain environment to vibrate in, much like how a guitar string needs a guitar to produce sound. This is where the concept of extra dimensions comes into play. Now, brace yourself. String theory proposes that our universe could have up to 10 or 11 dimensions. Yes, you heard it right. 10 or 11. But why don't we see these extra dimensions? Well, that's one of the many intriguing questions string theory brings to the table. The answer might lie in the concept of compactified dimensions. Simply put, these extra dimensions could be so incredibly small and tightly curled up on themselves that they're virtually impossible for us to perceive in our everyday lives. Think of it this way. If you look at a garden hose from a distance, it appears two-dimensional, but get up close and you'll see it's actually a three-dimensional cylinder. Similarly, these extra dimensions could be hiding in plain sight, beyond the resolution of our current scientific instruments. So, while we navigate our lives in a seemingly three-dimensional world, string theory suggests that there's a lot more going on beneath the surface. These extra dimensions, invisible and imperceptible as they may be, could be integral to the fundamental workings of the universe. And remember, this is not some far-fetched science fiction. This is a serious scientific theory that's being explored by some of the brightest minds in physics today. It's pushing the boundaries of our understanding and challenging our perceptions of reality. So, we might be living in a universe with more dimensions than we can see or feel. How does string theory explain the creation of the universe? This question takes us on an intriguing expedition into the realm of strings and the Big Bang. The Big Bang theory, as many of you well know, speaks of a singular point of infinite density and temperature that exploded, giving birth to our universe around 13.8 billion years ago. But in string theory, the picture is slightly different. String theory, with its multidimensional framework, offers a fascinating perspective on the Big Bang. The singularity, that point of infinite density, doesn't exist in the string theory narrative. Instead, we have a pre-Big Bang phase, a universe filled with strings vibrating in a high-energy state. But what triggered the transition from this high-energy state to the universe we observe today? This is where the concept of branes comes in. In string theory, our universe may exist on one of these branes, and the Big Bang could be the result of a collision between two such branes. When these branes collide, they release energy, resulting in the expansion and cooling of the universe, a process that eventually leads to the formation of galaxies, stars, and everything we see around us. This explanation, if proven, could provide a comprehensive description of the earliest moments of the universe, moments that the traditional Big Bang theory struggles to explain. However, it's crucial to note that these are still theoretical propositions. String theory, despite its elegance and potential, is yet to be empirically confirmed. It's like a beautiful symphony waiting for its notes to be validated by the orchestra of the universe. But even with its unproven status, string theory continues to offer thought-provoking insights into the mysteries of our universe. And perhaps the most intriguing of these insights is the idea that the Big Bang isn't the absolute beginning, but merely a transition. In the context of string theory, the Big Bang might just be another transition phase of the universe. Why is string theory still a theory and not a fact? That's the question we're grappling with in this segment. The challenge of proving string theory lies in our current technological limitations and the sheer enormity of the energy levels required to observe these minuscule strings. Imagine trying to spot a single grain of sand on a vast beach, but this grain of sand is not only infinitesimally small, it's also constantly vibrating and moving in multiple dimensions. That's what we're up against when trying to prove string theory. You see, these strings, the proposed fundamental building blocks of our universe, are believed to be about 100 billion times smaller than a proton. To put it into perspective, if a string were the size of an average tree, a proton would be the size of the entire solar system. And observing something so tiny requires an astronomical amount of energy, far beyond what our current particle accelerators can generate. The Large Hadron Collider, the world's most powerful particle accelerator, can reach energy levels of around 13 trillion electron volts. But to observe a string, we would need an accelerator that could reach a whopping 1 billion electron volts. That's a scale of energy that's simply mind-boggling and currently out of our reach. Another challenge stems from the fact that string theory predicts the existence of extra dimensions beyond the customary 3 dimensions of space and 1 of time that we're familiar with. It's difficult to conceive, let alone prove, the existence of these extra dimensions. Despite these challenges, physicists continue their quest to unravel the mysteries of the universe. They work tirelessly, pushing the boundaries of what we know and what we can prove. While string theory presents a compelling view of the universe, proving it remains one of the grand challenges of modern physics. Despite the challenges, why do physicists persist with string theory? A fascinating question indeed. It's not the simplicity of string theory that captivates these minds, it's the alluring promise it holds for the future of physics. String theory in its essence is a theory of everything. It attempts to weave together all fundamental forces of nature, including gravity, into a single unified framework. But beyond this, string theory holds the potential to shed light on some of the most profound and perplexing mysteries of the cosmos. Consider gravity, a force we're all familiar with, yet remains an enigma at the quantum level. In string theory, gravity isn't treated as an outlier. Instead, it emerges naturally from the vibrations of strings. This could provide a quantum-level explanation for gravity, a breakthrough that could revolutionize our understanding of the universe. Then there's the enigmatic dark matter. This invisible stuff makes up about 85% of the matter in the universe, yet we know almost nothing about it. String theory suggests that dark matter could be made of strings vibrating at a frequency that we can't currently detect. If true, this could lead to new ways of detecting and studying dark matter, and perhaps even harnessing its properties. String theory also promises to shed light on the birth of the universe itself. The Big Bang theory tells us that the universe began as a hot, dense point, but it doesn't explain what triggered this explosion. String theory, with its extra dimensions and vibrating strings, could offer insights into the conditions that sparked the creation of our universe. These are just a few examples of the unsolved mysteries that string theory could help unravel. The promise of string theory isn't in its complexity or in its abstract beauty, but in its potential to deepen our understanding of the universe and its workings. String theory may be unproven, but it holds the promise of a deeper understanding of the universe. And that, dear listeners, is why physicists persist with it. What does the future hold for string theory? A tantalizing question indeed. As we peer into the future of string theory, we find ourselves on a landscape teeming with possibilities and potential breakthroughs. The future of string theory is promising, to say the least. It's a realm of physics where the only constant is change, where the only certainty is uncertainty. Right now, there are numerous ongoing research projects around the globe that are pushing the boundaries of our understanding of string theory. In the world of academia, scholars and scientists are building upon the foundational work of their predecessors, seeking to refine and redefine string theory. They're exploring new mathematical models, developing innovative computational techniques, and diving deeper into the quantum world than ever before. They're challenging the status quo, questioning the established norms, and in doing so, they're paving the way for groundbreaking discoveries. But academia isn't the only arena where string theory is making waves. In the world of technology, advancements are being made that could potentially provide the tools necessary to test and possibly prove or disprove string theory. From quantum computers that could simulate string interactions to particle accelerators that might someday be powerful enough to detect the elusive strings themselves, the future of string theory is intertwined with the future of technology. Yet, it's important to remember that the future of string theory, like the future of any scientific theory, is not predetermined. It's shaped by the efforts of countless individuals, by the progress of technology, and by the unpredictable twists and turns of discovery. It's a future that's written in the language of strings, a future that's waiting to be unspooled. So, what does the future hold for string theory? The answer, quite simply, is that we don't know. But that's the beauty of it. That's the thrill of the chase. That's the allure of the unknown. Whether string theory will be proven or not, it will continue to fascinate us with its intriguing view of the universe. So, what have we learned about string theory and the universe? We've embarked on a journey through the cosmos, through dimensions unseen, and through the very fabric of reality itself. We've ventured into the realm of string theory, a theory that suggests everything we know, everything we see, and everything we are is composed of tiny, vibrating strings of energy. We've grappled with the concept of a universe not made up of particles, but of strings. Strings that vibrate at different frequencies to create the symphony of the cosmos, the music of everything that exists. We've learned that these strings, infinitesimal though they are, could be the key to unlocking the mysteries of the universe. We've explored the concept of dimensions beyond the three we know: height, width and depth, and time. String theory proposes that there could be as many as 11 dimensions that could hold the answers to questions we've yet to even ask. We've looked at the origins of the universe through the lens of string theory. How the Big Bang might have been the result of a collision between giant cosmic strings, setting off a wave of energy that gave birth to the universe as we know it. We've contemplated the challenges that string theory faces. It's a theory that, as of now, remains unproven. The strings are too small to detect, the dimensions too hidden to see. Yet the mathematical elegance of the theory and the way it unifies the laws of physics keeps the flame of curiosity burning. We've pondered the future of string theory. Will it be proven or disproven? Will it remain an elegant mathematical framework, or will it become the accepted model of reality? Only time will tell. String theory offers a fascinating perspective on the universe. As we continue to explore it, who knows what secrets we might unravel about the nature of reality.